Good day, folks. This is Amir McKean, electrical engineer, author, publisher, and founder of AICpublications.com. And welcome to another tutorial in our 10-minute engineering program. This is the place where we demystify the math and simplify the science. So if you are someone who has an inventive mind, an innovative mind, you have an engineering mind, or you have a child that has a mind like that, no matter how young or how old, you are in the right place. If you've ever wondered about technology and how to get in front of it, how to understand it, how to be able to use this to make a career change for yourself, this is the place for you. Today's tutorial that we're going to be over is we're going to be taking you over the basic integrated circuit. And we're going to be using one of the most widely used integrated circuits. It's called the 555 timer chip, and we're going to be using it in an astable mode. That is a fancy term for meaning we're just going to be able to output one pulse at a time. And the pulse is going to be indicated by a light emitting diode. And that's how we'll see the pulse on that. And we'll be able to have a timer hooked up to the circuit so that we can actually verify that what we've done is correct. So I will take you through the actual circuit that we've designed right now. First, let me explain to you what an integrated circuit is. An integrated circuit is literally a tiny computer chip that has thousands, if not millions, of circuits inside of it. And those circuits that are inside of it can be used in many diverse ways. But the pin or the chip itself, the integrated circuit chip itself, may have anywhere from 8 to 16 to 24 or 32 pins. And the more circuits that are inside of this tiny chip, the more applications and the more uses that it has. And you have a various array of integrated circuits. You have the 555, you have operational amplifiers, you have different sensors, you have temperature sensors, you have voice modulators, and the list goes on and on and on. And throughout the various series of this 10-minute engineering program, we will take you through some of them. So first, let me explain to you what we did with this circuit. Up in the left-hand corner, you're going to see everything is powered by a 9-volt battery. Then we have R1, which is a 560K ohm resistor. And we have R2, which is also a 560K ohm resistor. And both of those run in conjunction with a 10 microfarad capacitor. This configuration with these two resistors and the capacitor, that is what creates the time constant that controls how long the light will pulse. On the output side, which is pin 3, which you see indicated by R3 and the light emitting diode. Now, the reason that we have R3 here is that R3, anytime that you use a light emitting diode, you always want to have something that controls the current and makes the light emitting diode not get too much current so that it won't burn out. So that's the purpose of all of these. And what happens is this time constant that's created by the combination of the resistors and the capacitors, the capacitor is going to charge up to a portion of the battery voltage, and then it's going to discharge according to the time constant, and that discharge is what's going to turn on the light emitting diode. So let me take you right now through the actual circuit itself so that you can actually see what we've done in the lab. All right. And if you can see here, we've got our timer that we're going to turn on once we turn the battery on. You have your light emitting diode that's going to indicate how long the pulse is. We have our 600 ohm, which is actually a 560 ohm resistor, which limits the current. We have our 560K resistor here. We have our second 560K resistor here. And then that goes down in series with the 10 microfarad capacitor here. Here we have the 555 timer chip, and all of this is connected and configured the same way that we showed you in the circuit. So what I'm going to do is turn this on, and we're going to wait until the light turns off. And then the second time that the light turns on, that's when we'll start the timer. And then we'll see how long the light stays on and how long it stays off. All right. So we've got the light on now, and I'll wait till it goes off. And then once it goes off, we'll hit the start just to count. Okay, so that's about 3.5 seconds that the timer stays off, or that the pulse stays off. So we'll clear this, and we'll wait till the next time that the light comes on, and then we'll actually set the timer again to see how long the pulse is. And there we go. And we've got about 7.6 seconds that the circuit's pulse stayed on. So let's go back. And we will get back in here and go over and verify how this worked. Now, as we stated before, the LEDs turn on with the correct voltage. The pulse, or the blinking speed, was controlled by the resistor and the capacitor. The capacitor, in this instance, it does create an open circuit voltage, but it also does charge the capacitor as well in this particular application. And let me go over this math. That way you can see it just a little bit better there. And as we always say in our tutorials, what does the math say? Because we do know that the math talks to us. We just have to understand why the math is applicable here. So as I told you before, the recombination of the resistor and the capacitor create a time constant. So this is the actual formula that's creating how long the capacitor charges, i.e. how long the pulse stays on and how long the pulse will stay off. So the formula here is just we take 0.693, multiply that by the addition of both resistors, and then multiply that by the capacitor. And we end up getting 7.8 seconds, which means in the perfect condition, the pulse should stay on, or the light should stay on, no more than about 7.8 seconds. And if you recall, the test that we did in the lab, the pulse actually stayed on, or the light stayed on, for 7.6 seconds. So that works. The off time formula calculated is 0.693 multiplied by the second resistor multiplied by the capacitor. And that comes to about 3.9 seconds. And if you recall, when we used our timer, the off time of this pulse was about 3.5 seconds. Now, in a perfect world, we could hook a timer to the actual circuit and get it down to the millisecond and microsecond, and we would get these a little bit more closer. But this works, so we can see that our math is correct, and it validates the design, and it validates the functionality of this integrated circuit. So the thing that's important here is understanding how to get comfortable with integrated circuits, understanding how to get comfortable with the combination of the resistors and the capacitors and the different applications in which they apply. So the applications that you're seeing here, we use this as a delay circuit. We use this as a way to determine how on we want something to be in terms of time, how long we want something to be off. And you can see this in alarm systems. You can see this in alert systems. You can see this in a myriad of applications, not just this particular way. This circuit also helps you understand how the mathematical equations help to work together with the different components of the resistors and the capacitors in order to determine how we can use them to actually control different mechanisms of an electronic circuit. So we hope we've helped you on this. You can reach out to us with questions at submissions@aicpublications.com. If you go over to our website right now and join our subscriber list, you can get a free book where we detail the different components of technology, and you'll be able to get real-time updates on what we do and the content that we offer in all the different platforms that we're available. All right. Again, my name is Amir McKean with AICpublications.com, where our motto is that we want every member of our customer base to attain the knowledge, innovate for success, and command the future. Till next time.